This meeting is being recorded. Good afternoon, everyone. Can we go ahead and get started? My name is Elena Stepanidis, and I'm a program executive in the Chief Science Data Office at NASA headquarters. And I'm co-chairing the Science Mission Directorate Data and Computing Architecture Study with Mike Little. I'm really excited that we have James Colliander today from 2I2C here to speak to us. But first, I just want to hand it over to Kevin Murphy, who's NASA's Chief Science Data Officer, for just a brief introduction to what we're doing here in the study and what we're doing with open science at NASA.
A little technical difficulty with my camera, but I'll just use the one that's working. So yeah, thank you, Elena. Thank you, James. I think this will be a great presentation. So first, a little bit of context here. We're kicking off a data and computing architecture study to find ways to better coordinate high-end computing and cloud computing within NASA. As we prioritize open source science, which is kind of NASA's implementation of open science, I think now is really a critical time to evaluate if we have the right coordination between our on-premise and cloud-based systems. Next slide, please. So the scope of the study, just for your knowledge, is that it includes data and computing systems supported by SMD, including scientific modeling, simulation, data processing, analytics, AI, ML, or any of the newer kind of techniques that we use. It includes all of the kind of the funded activities you see below. Next slide. We have a code of conduct for all of our open meetings because part of open science means that we are open in a lot of these deliberations and discussions. So that just means that we have people that attend that from all over the place. So we want people to be treated with respect and dignity and consideration of their opinions. We want you to be collaborative. We want you to be open, critiquing ideas rather than people or individuals. Avoid personal attacks. Be mindful of the surroundings. Alert us if you see anything dangerous or someone in distress. All right. In terms of unacceptable behavior, things like harassment or intimidation, discrimination in any form will not be tolerated. Verbal abuse, and you can kind of see the specific examples there, but we ask you really not to disrupt the panel during these discussions and lightning talks and other things, so that we can continue to have open meetings and open discussions. Next slide. So now I guess I hand it over to Peter.
Yes, thank you, Kevin. Hello, everyone. Welcome to another of our series of workshops for this study. As with our previous workshops, I'll be helping to moderate the discussion and bringing questions forward. We had a little issue with our NASA tool that we've been using. So our fallback today is that we're simply going to use the WebEx chat, and several of us will track those questions and make sure we get those brought forward. So please, when we get to the question and answer, just use the chat, insert a question. It might help if you have a specific question, maybe just put a Q in there, just so we can see that and not think it's just a part of the chat. Next slide, please. Well, it is my pleasure to welcome Jim Colliander. He is 2I2C's co-founder and partnerships lead. Today, we're going to get an overview of 2I2C's work seen through an open source science lens. We'll also talk a bit about user needs and business needs that are likely relevant to SMD's transition to open source science. We'll also talk about best practices available through 2I2C's, identifiable through 2I2C's work, and insights regarding a data and computing architecture. Jim Colliander is a co-founder of 2I2C and partnership lead. He's also professor of mathematics at the University of British Columbia. Previously, he served as director of the Pacific Institute for Mathematical Sciences, PIMS, While at PIMS and using infrastructure from Compute Canada, he helped create a national scale Jupyter Hub service called Syzygy. I hope I pronounced that right. It's got a lot of consonants. He's also has co-founded Callisto, a collaboration between PIMS and Cybera. Callisto develops open education resources and training programs for students and teachers in grades 5 through 12, leveraging cloud-hosted interactive computing. He also co-founded Crowdmark, an education technology company based in Toronto that provides workflows and AI-based improvements to education assessments. It's my pleasure to introduce Jim Colliander. Thanks, Jim.
Thanks, Peter. It's a great honor to be able to speak to you and this audience. I am very excited to set the stage for what I hope will be a really exciting conversation. This is a really special moment, I think, for NASA, and I congratulate NASA on leading the Year of Open Science launch for 2023. And that's the start of hopefully a century of improved accelerated science. And it is, for me, kind of raises the hair on the back of my neck. I get so excited about the fact that I get to interact with folks at NASA. And I'm really honored to be able to be here to present with you. So I'm going to attempt to share my browser screen. So are you seeing some slides that say building the modern science stack?
Yes, we are.
Great. So with my way of seeing WebEx, I don't have a very clear way to see all the chat and so forth right now. So I would encourage any of you to interrupt me as you see best as I go through the slides. So as a framing for this, I think that we are now kind of building the analog of something people are saying in, let's say in the startup world, the modern data stack. I think we're exploring ideas to build a modern science stack, and this compute data architecture study that you all are engaged in, I think is a great time to reflect on prior ways of doing things and to imagine future ways that we might do things differently in order to accelerate science and get more folks to participate in science. So can you see my mouse also? I'm curious if that's coming through.
Yes.
Yeah.
Great. So there is a hyperlink here. If you go to bit.ly, SMD-architecture, you will come to a rendered version of my slides as well. So I invite you to grab that link if you wish. What I'm going to talk about is the problem that we're trying to solve and the opportunity. I'm going to make some general remarks about science. And from those general remarks, I'm going to try to extract guidance and principles for how I think not just the data architecture, to how we should be thinking as a global enterprise around transforming science. So that's my section on guidance. And then I'll extract a few observations about what we've been doing at 2I2C and how I think those observations might be relevant for your study. And then I dumped some other slides, most of which are slides that I created for a talk that I gave to the Jack Eddy Symposium in June of this year, in the event that they become relevant to the subsequent conversation that we have. So the problem that I think we're trying to solve is a little paradoxical. I think science is underperforming relative to its potential. And this is kind of silly to say because I think science is performing today at as high or at the highest level it has ever performed previously. So how can we describe it as underperforming? Well, I think we all know that there are underrepresented groups of people in science. I think we all know that there are certain privileges and advantages that folks that are affiliated with R1 universities get to do that others can't do. And I think we are also all aware that there are some scientific communities that are more stingy with their data and their ideas than others. And while science may be performing better than it ever has in the past, that still doesn't mean that we've optimized the potential for science. And this call to action from NASA TOPS, from the Open Source Science Initiative, and from other similar voices, I think is a call to action for us to reflect on what science is and figure out ways that we might be able to work together better to advance on the goals of science in a more effective way. So we have an opportunity, and I think this is kind of where this opportunity sits. There may be ways for us to combine advances in technology and advances in what I'll characterize as social innovation in order to boost the output of science. And how to capitalize on these technological and social advances to move science forward, I think is part of the thrust of your study. And it's also part of what I perceive to be the thrust of the Open Source Science Initiative. This is a massive bleeding head wound problem, even though we may not perceive it as such, because science is performing so well today. But when we look around at the challenges associated with misinformation, the challenges associated with climate change, we have a massive need globally for a high performing science ecosystem. And reflecting on the ways that it's currently performing and figuring out ways to make it perform even better is a very important activity for all of us to be engaged in. There is an immediacy. This is very similar to what Kevin was saying at the top, that there's a special moment now for us to engage in planning for a transformation of science, to not be passive participants in the ecosystem that we belong to, but instead be active participants that are working to transform the ecosystem that we belong to. There are a variety of signals that I'll mention in my talk that forecast we are already in a process of transformation. And there have been significant investments in a new vision for a future science that is frequently captured under this word open. And as far as I see it right now, this notion of a future state of science that is more open is really a work in progress. And NASA is helping to define this future state, but I think we're really engaged in a process of bringing meaning to this adjective. But I also want to emphasize that that's an adjective. Science is the noun here, and we're really trying to advance science. And the way that we open it and make science better is what we're trying to accomplish. But we're really trying to advance something that we know very well, which is science. So we may be at an inflection point. And that this year of open science and this activity from NASA TOPS, from the UNESCO recommendation, and other sources like in Canada, we have the roadmap to open science. There is kind of a recognition on the part of government agencies that ideas that may have initially started with open source software have kind of propagated throughout the rest of the science stack and are now taking root in a grassroots way and growing up. And there's kind of a top to bottom unification of effort. I think some other growing activities that are causing this point of inflection, the sophistication in interactive computing tools like those that 2I2C deploys signals that the ecosystem for collaboration is at a transformation point. And there are new ways that we are trading information as scientists and as consumers of scientific advances. And there's kind of discussion towards kind of a commons-based way of setting up new incentives for science. There's a very influential book, I think, from Benkler in 2004 that called for this kind of a transformation, but it's taken quite some time, I think, for the rest of science to kind of catch up to Benkler's vision. But now we have it happening in, I think, a quite significant way. So just some framing questions that I'm reflecting on as I prepared these slides and these remarks for your study. How should NASA configure data and compute architecture? What are the principles that should guide that possible reconfiguration of NASA's digital information ecosystem? On what time frame should we see this kind of a transformation? I'm often thinking about this famous quote due to Bill Gates that says, people tend to overestimate what they can accomplish in a year, and they tend to underestimate what they can accomplish over a decade. And when I think about NASA, I think about the foundational decade of the 1960s. And so as I imagine the transformation that we hope to catalyze with the Year of Open Science, I'm thinking of it either on a decade time scale or on a generational time scale. I think these kinds of transformations that we're talking about are extremely significant, and they're not going to happen in a quarter or a year, but I do think that we should see signals in that type of time frame, say in a year. We should see significant changes by, say, AGU 2023 after all of the investments that are being made right now. And what is it that we measure to say that there has been a transformation? I have various answers to some of these questions, but I think these questions can frame some of our conversation later. So let's talk a little bit about science, since it's this enterprise that we hope to open up. So what is science? So my definition of science is that it's a systematic enterprise that builds and organizes human understanding of the universe with testable explanations and predictions. And the central activity that we as scientists engage in is exchanging information. We exchange information when we train our students, when we work together with our collaborators, when we act as peer reviewers, evaluating the work of others, when we act as panelists that are trying to contribute to conversations like this one. So really, science is a human enterprise that's focused on trying to bring people together with shared ways of logically understanding things, and with those shared ways of testing nature and thinking about important questions about the universe, we collectively advance our understanding of the world that we live in. What I want to emphasize about science here is that it's a social enterprise. It's groups of people working together in different ways, and the way that we bring together these social activities and manage these social collaborations is really through different structures of governance. And so I view that as very much related to the call in the study. It's not just about the way that the transistors work, but it's also about the way that we configure categories of users, expectations, workflows, gamifications, how we work together to get this science done is also part of what's happening on top of the digital tool chains that you're exploring. So a really nice quote emerged a couple of weeks ago in the TOPS community panel that took place at JPL that I captured onto Twitter. My 2I2C co-founder colleague, Fernando Perez, just said at one point in the discussion that open science is a process, not a product. And I want to emphasize those workflows, that activity, the processes by which humans engage together is what I think we're trying to influence through this opening up of science. And it's not just the products or the PDF articles or the data sets that come out of our instruments. It's all of this collective effort that brings us together towards trying to understand nature. So I think of this sometimes in a frame using language that's been pioneered by Elinor Ostrom, thinking of science as a commons. So the people that work in these social collaborative structures, sometimes organized under universities or under agencies within academic societies. Some of these people are engaged in philanthropic activities. We have publishers, we have research teams. So we've got all these people organized in various kinds of structures working to try to understand nature. And then we have resources like salaries and instruments and satellites and rovers and libraries and data and compute. And the way that we distribute the resources to the people and the way that we reward the people that are doing well and celebrate the people that are doing fabulously is really the way that we structure governance and the way that the scientific enterprise is organized. And while science may be performing as well as it ever has, it doesn't mean that it's performing as good as it potentially could. And I think that in addition to the technology advances, we have to think about the way that governance is implemented through these technologies. I want to emphasize that science is not static. Science as an enterprise has changed and is constantly changing. So when I was a graduate student in the library at the University of Illinois in Urbana-Champaign, there were these little cards that you could fill out, little postcards, and you could send them away requesting a reprint of an article that you thought was interesting. And I had professors that bemoaned the emergence of the internet because they didn't get the signal on how good their work was because they weren't getting these postcards asking for the reprints. But now you can just download papers. So that's just an example in my lifetime of a way that I think science has transformed. There's many other ways that the internet has driven changes to science. There was no National Science Foundation about 80 years ago. And the entire structure of modern investment in supporting research is a relatively modern invention. I think that we as scientists took a passive approach to the emergence of the internet with devastating consequences. So publishers set up paywalls, created games associated with impact factors, and a mathematician that I think highly of has created this website and this movement called Cost of Knowledge that's kind of measuring the impact of hiding our scientific products behind paywalls. And of course, we've seen the open access movement that goes against that. The pace of change can also be appreciated if you remember that the iPhone emerged only 15 years ago, and opportunities for citizen science or the Internet of Things connecting human beings' hands to essentially virtual ubiquity with all of the digital infrastructure that's around us has really propagated quite quickly in just recent times. So my area of mathematical research is on Hamiltonian partial differential equations. So things are changing a lot in the dynamical systems that I study, but I have found in my thinking about mathematics, especially when things are really dynamic, is that if you can identify aspects of the dynamical system that are monotone, meaning they're constantly decreasing or they're constantly increasing, or conserved, meaning they're kind of universally the same all the time, like energy or like mass in some of the problems that I study, then these insights allow you to sort of set a toehold that allows you to do things in the presence of something changing very rapidly because you make your structures, assumptions, and ways to try to control the unfolding of the future attached to things that you actually know are changing in a deliberate way, like monotonicity, or changing without changing at all, like conservation. So as I reflect on all of this dynamic in the way that science has evolved, I also want to extract some principles that are kind of universal, that are either monotone or conservative across the dynamics of science as a dynamical system. So the first thing I want to highlight is that science works. It's extremely effective. There is massive return on investment in science. And I think this is underdeveloped in the conversation by scientists towards policymakers, notwithstanding these Golden Fleece Awards and whatever William Proxmire tried to propagate. Science is just devastatingly effective. And we have to celebrate that and ask for more investment because modern society is built on the advances that have emerged from this collective enterprise of trying to understand nature. So that's a constant fact. Investing in science generates massive returns for society. The core activity, as I hinted at above, is the exchange of information. And we may change the methods by which we communicate, but it's inevitable that we're going to keep exchanging information. And so we might want to think upon that as a core activity that we should rally around and figure out what types of information should be exchanged. Who are the listeners? Who are the speakers? How should we store this information? Science is a multi-generational effort. We have people with gray hair, often with a lot of expertise and wisdom, training younger people who might be very ambitious, excited to understand. But science from the time of Plato's Academy has been this multi-generational effort. And we've seen an evolution, that's not rendering, there it is. There's been an evolution in the history of universities, going back from the time of the University of Bologna and ancient Cambridge and Oxford to modern instantiations like UNAM in Mexico City and the modern German-style university at Johns Hopkins built on the work in Berlin by Werner von Humboldt. And so these structures of the way a university is configured to support this multi-generational effort has also transformed, but we have this constancy that there's always training involved, always education involved. There are also some persistent tensions that I think are universal across all of science. There's a tension for an individual to get rewarded versus an entire field to advance. And so there's this collective versus individual tension. I think there's a tension around specialization versus generalization. My subject has pioneers that invented new things called computers, but my subject kind of conceded the subject of studying computer science to a new discipline. And I think there are also significant tensions between the dreams that we want to do, the large scale experiments we want to run, versus our capacity as a society to invest enough or to bring together the people in a concentrated way to fulfill those dreams. So these tensions are also kind of persistent and inevitable, and we can build open strategies about science knowing that this is going to be there no matter how technology or social innovation transforms the way we do this work. One last thing that I think is kind of universal about the history of science is that the formalization of pattern recognition has been a persistent way to accelerate discovery. So whenever you mathematize or add computation or include more data into a subject, the subject transforms and may become a new subject. The addition of genomics information, for example, to the study of biology with computational backing spawn a new field, bioinformatics. And if you take adjectives like precision or smart or digital, and you put them in front of any other subject like health or agriculture or sociology, you generate new subfields that are right now, I think, exciting areas right at the knowledge frontier. So this mathematization or computational enrichment of prior subjects of study is creating new pathways to advance the historical disciplines of study in faster ways and facilitates new ways to collaborate. So the next section is some ways to think about how the data compute architecture at NASA, and more generally, how science at NASA should be configured to achieve these goals of openness. So the first thing is an intellectual virtue. I think the virtue that should be guiding science is intellectual generosity. We should be sharing our ideas. We should be helping others to understand, because the core mission of science is to advance human understanding. It's not for me to get a bigger H-index. The goal of science is to try to advance human understanding. And that's really an outward way of thinking about others and trying to help others to move forward in that understanding. So I have two links there. I'm very influenced by this essay by William Thurston, where he kind of explains how he has a philosophy of mathematics that I find to be intellectually generous. And then Morris is a philosopher who reflects on Thurston's essay and frames Thurston's contribution within this virtue of intellectual generosity. And I have found those to be very influential. Another virtue that I think should guide the way that we are building systems to support science is intellectual humility. So I am the product of previous ancestors that have set in motion this pattern of life. So I have certain humility just being a human organism living today in the wake of all that precedes me. But I'm also a scientist, and I recognize that I am the privileged beneficiary of fantastic ideas and advances that others have brought forth. And one way to picture it is this kind of viral graphic that evokes what it means to be a PhD student, or what it means to make a PhD thesis. So as you go through the sequence of circles here, you imagine this circle that contains all human knowledge, and then you have a growing sort of thing at the center of the egg that's explaining the process by which you learn as a youngster. And then you start to move towards the edge of knowledge in, say, graduate school. And then finally, you just advance a little bit beyond the edge of human knowledge with your PhD. That contribution is something we celebrate. You know, Dr. So-and-so, congratulations. But the real contribution of that PhD, that small advance on the sphere of knowledge, it is small relative to the global collection of all of the knowledge that it's built on. And I think if we reflect with humility, I think we do a better service to all that science is. So I think intellectual humility is another virtue that should guide a lot of what we're doing. There are also some really interesting axioms developed by Ardila, a mathematician from San Francisco State, which are really axioms about human talent. So I'm going to rephrase these slightly than way Ardila did by replacing mathematics with science. So scientific potential is distributed equally among different groups, irrespective of geographic, demographic, economic boundaries. Everyone can participate in science, and science is this powerful tool that can help us understand our relationship to the universe, and it can be used in different ways by different communities. And every student, I would maybe even go so far as to say every human, deserves to be treated with dignity and respect, and allowing that person to grow and learn in science, I think, is one of these talent axioms that should guide the way that science becomes more open. So another guiding principle emerges from this notion of the information exchange as the core activity of science. So basic needs, basic human needs like the need for shelter, drive choices about what we recognize as fundamental human rights. So the history of the Bell system, maybe I can say more about this if folks are interested, involves an argument from the pioneering CEO at the turn of the 1900s that humans have a fundamental need to connect with one another. And this CEO, Theodore Vail, argued that there should be a right to telephone access. And that argument that telephone access is so fundamental to human needs was kind of the underlying argument that allowed the Bell system to propagate as a monopoly for quite some time. But we have other rights as humans. We have the right to read, we have the right to education, and I would argue that the explosion of data and the ways that we want to understand our relationship to nature boils down to a kind of undefined or in the process of being defined right to participate in science. And the terms of that, I don't think I've fully developed, but I think it's a very interesting concept to try to explore. We should all have access to the tools necessary to understand data. If you contrast this with other things that are in society, we appear to have the right to carbon energy. We are all given the opportunity to go buy gasoline, but it hasn't really been defined that way. And if you think about the right to participate in science in a similar way to our right to transportation or our right to move through the world, then maybe there's something here that NASA could reflect on and provide some leadership on. I think we need to define a right to participate in science. So who are the audiences for NASA's data compute architecture? Certainly it includes NASA personnel, but does it also include youngsters that are growing in excitement about their relationship to the universe? And what are NASA's obligations to these audiences? And how do we balance this right to participate in science with the costs required to make sure that the tools necessary for participation are paid for? And these are significant challenges, and I don't have all of the answers, but the fact that almost everyone has a smartphone means that a lot of the costs associated with participation are already covered. And so we might be able to find ways to mobilize data and mobilize engagement in the scientific enterprise in new ways that expand the entire ecosystem and really lead to advances that are crucial to our humanity. So how do we play with these social innovations and technological inventions? How do we design the future of science? So I reflect on the fact that we are at the 75th anniversary right now of the invention of the transistor. And it's also the 75th anniversary, essentially, of the information age, of information theory developed by Claude Shannon. So the notion of a bit to quantify information was invented about 75 years ago. So if you were sitting in Bell Labs in 1949 and imagining the future that would be built around the newly invented transistor and all of these advances in the information age, you might imagine how the future will unfold. And essentially what's developed is a whole bunch of equity-backed for-profit startups have developed the technology and social systems in the wake of these inventions. But there are also some collective structures that have emerged in this design space. So we can contrast, say, Facebook and Google and Wolfram with, say, the Linux kernel or Wikipedia or the scientific Python stack. And some of these are more open and collective, and others of these are more closed and intellectual property based. But I encourage, as part of this study, to reflect on what are the incentives for creating social plus technical advances that support science. I think that some principles here are we should avoid vendor lock-in. No one should own the letter K. No one should own the ways that scientists communicate. And scientists should be actively engaged in defining the terms of engagement, the league, the roles, the rules of the scientific enterprise. I think that we made a mistake as an organization of scientists in the way that the digital ecosystem was used in the late 90s and early 2000s, leading to the open access crisis. And last thing I'll kind of reflect on here is 2023 will probably be looked back upon as a transformational year of open science, but it may also be quite similar to the year 1947, 1948, when the transistor was invented. Perhaps next year we will finally have robust qubits, and then there might be a new era of quantum information. And if that unfolds, I think it would be very useful to have these kinds of guiding principles that are anchored in the core understanding, the fundamental aspects of science, so that we don't lose sight or lose opportunities the way we've done with some aspects of the digital era. So just finally, a few observations. I think I'm running a little long, but I'll wind down in just a moment. In my experience with Syzygy, which is a national scale resource for Jupyter Hub access in Canada, and Callisto that was referenced by Peter at the introduction, I think it is the case that there will be national scale open tool chain for scientific or data intensive work. I think that's inevitable. But what that looks like and how we take advantage of this national scale tool chain, I think is something that should be reflected upon in the course of your study. How do we pay for it? Who should get the access? How do we granularize or make different levels of compute available to different audiences? No one should own the scientific tool chain, but not everyone should have access to, the latest from NVIDIA with massive powers at AWS. So how do we distribute some of this across the ecosystem of various user audiences? So 2I2C is a defensive strategy to protect the digital tools for science. And one of the ideas that we've developed, which I think has been very interesting to watch unfold, is this concept called a right to replicate. I view this as a kind of precursor to this larger right to participate. But 2I2C offers infrastructure for scientists working together on the cloud. And we do so with this right to replicate. So the infrastructure that delivers, say, Jupyter Hub is publicly accessible, and it is written in such a way that our customers could leave 2I2C, take the playbook that we used for delivering their resources, and operate it themselves. We do so in such a way that this infrastructure could be run on any of the major commercial cloud platforms. And in so doing, we make commercial cloud into a utility, and we avoid being locked into Google versus Azure versus AWS. This right to replicate also creates a pathway for federation. So if some of our customers choose to no longer use 2I2C as their infrastructure manager, and they want to do it themselves, then that means that there's new talent in managing these site reliability engineering methods for delivering these types of tools, which makes science more robust. We also deliver it in such a way that there's no purity test like the GNU public license. So the right to replicate allows the use of closed source tools, but it forbids the use of closed infrastructure. So it's a kind of subtle way that navigates through a lot of licenses that I think is a significant idea in enabling toolchain propagation and toolchain federation. I've also observed that there's kind of an emerging phenomena where communities are attracted to digital watering holes. So the data sizes are getting so big that you can't download the data. So the data is sitting on, say, commercial cloud. So we put tool chains adjacent to the data and then facilitate communities to interact with the data through those tools. And communities like the Pangeo community, the International Committee of Investigative Journalists, the Alabama Water Institute has launched a Jupyter Hub with help from 2I2C that's looking at a multi-stakeholder community to manage the national water resource. And there are similar activities going on in NASA communities focused on heliophysics, such as HelioCloud and the cryosphere community. So these virtual research environments are science gateways, are kind of a new way to bring people together. And it's being driven by a variety of forces, such as the power of the cloud, and the need to put cloud tools next to the data. These platforms are multi-purpose. So they provide pathways for new talent to get trained, for folks to explore and play around with ideas, for people to collaborate in new ways. These platforms also facilitate dashboarding so that someone who maybe doesn't have the coding expertise can nevertheless see a slider or see a visualization so they get some insights. There's new ways to basically tell scientific stories, and through this, there's a faster way to reproduce research and validate research advances. These are also serving multi-stakeholder audiences. So from trainees to policymakers with researchers and people managing operations in between, you can have an advance that happens today based on data that was collected yesterday, read by someone next week, updated with new data because there's an API in the way that the story is told. And then next week, a policymaker may make decisions based on what's emerging from this API-based way of getting insights. This is a much faster way to develop knowledge moving towards operations than we've seen previously. So some other dimensions here. Do we have a polymath approach or a monomath approach? Are we thinking like system science, or are we working in narrow disciplinary Dewey Decimal System expansions? And these virtual research environments appear to cut across discipline-specific questions and are more like pathways to convergent research activities. The speed of knowledge transfer is changing. So knowledge is typically modeled through diffusion processes. But if you're in a room, at the front of the room, and you light a cigarette, and the only thing that's happening is diffusion, it might take a very, very long time for you to actually smell the cigarette. But in reality, the smell of the cigarette propagates in the room really quickly because there are these convective eddies that are moving the particles from the smoke to your nose faster. So I think a similar thing is taking place in knowledge, where we can make knowledge convect and it gets to the right people at the right time more quickly. And in so doing, instead of publishing a preprint, waiting for the peer review process, a year later the thing gets published, someone in a minister's office or in a congressperson's office reads the research and begins to influence policy. We can now accelerate this research to operations transition, and the transition from questions arising in operations being answered by research much more quickly by having scientific products that are reproducible and attached to the data that is driving the questions. With help from some folks in the cryo community, notably Matthew Siegfried and Tasha Snow, 2I2C has developed what I think might be an interesting template to consider. So we've launched a Jupyter Hub. This Jupyter Hub is going to be used through a sequence of events by the community of cryosphere researchers. And then iteratively through these events, we aim to improve the hub and improve the community dynamic on how they use the hub to advance research in the cryosphere community, with a target that at AGU 2023, this process of iteration will showcase a future for open science. And I think this model of a persistent virtual research environment combined with a collection of face-to-face and virtual events, iteratively informing how we're using tools and social innovation to improve the development of science. This is a template that should be considered by others and might be relevant for the study. My last is a call to action for the study. Instead of just doing an environment scan or a needs analysis, I encourage you to propose experiments during the year of open science. Can you launch time-boxed access for diverse audiences? Can you unify ongoing efforts, maybe by taking a system science approach and recognizing that heliophysics inputs drive climate in the high atmosphere. Climate in turn drives things that influence the glaciers, and the glaciers in turn flood down rivers and influence the national water management policy that the folks at NOAA are interested in. So are there ways that you can try to catalyze these multidisciplinary, multi-stakeholder system science ways of working together? What experiments can you imagine that would explore ideas on how storytelling tools like dashboards or Binder or ephemeral data plus compute technologies, how would that affect the goals of NASA's Open Science Initiative? And then last, I encourage you to also think about experiments that might incentivize validating other people's work, prior work, or reproducing and strengthening the advances of others. So I have other slides in case there are questions that lead me to try to jump down other rabbit holes, but I'll stop right there. And I'm sorry I went a little longer than was forecast.
No worries about the length. I can tell from the chat and everything. Folks were really grabbed by your talk in many ways. I don't know if you can see it, but we're seeing some claps over on the screen here, and the chat is pretty active, but also I think it's kind of quiet because people were listening to you. And I have to say, it was, oh, I'm sorry. Hearing you refer to Ostrom in a talk like this was just remarkable. So thank you for pulling that out. Really nice. Before we get into this, I want to offer James Mahoney says before he asks his question, and I think it's true for any of the questions, he just wants to thank you for this talk. Absolutely inspiring, some great wisdoms. And we're seeing people talking about rewatching it and all that. So thank you very much. We do have several really interesting questions. You spoke so directly to our normal framing questions that I'm going to jump back and forth and primarily draw from what's in the chat. Let me just start with one from Mike Little. He's asking if you could give us some thoughts on your vision of the role of commercial firms in open source science.
Oh, that's a good question. So I guess the first thing that I want to say, which I think is implicit in Mike's framing of the questions, is that we have to find a way to blend both. So there is no, I think we lose when we say there should be no intellectual property, there should be no commercial benefit. The profit motive has been a very effective incentive, and lots of value has grown out of the industrial market system. So I don't think there's necessarily an obstacle in any way to using those vehicles. But I think that since the time of the transistor, we've leaned into that side a little bit more than we had to. There are these exceptional cases like the emergence of the Linux kernel and the emergence of Wikipedia, which are more Ostrom-like, if you will, in their configuration rather than through an intellectual property equity-backed venture startup. And those models have turned out to be significant, but I don't think we have the same accelerator incubator complex that we see in the wake of Y Combinator, trying to build new versions of Wikipedia or new versions of the Linux kernel. So now maybe more to the heart of what's happening right today in Mike's question. I think that there is a significant problem in that open source tools for science are sometimes managed by a single individual who is overwhelmed by maintenance needs and not properly rewarded. So in some cases, those single individuals get to do this on the side of their desk within a commercial environment. And those commercial environments that support that individual appropriately should be celebrated. But I don't think we have the right approach. There's the emerging research software engineer role that's been kind of pioneered in the United Kingdom and is propagating elsewhere. But we don't have proper structures, I think, to reward open source contributors. So that's a few ideas. I may not have answered Mike's question in the framing that he wanted, and so please feel free to follow up, but those are some observations that I have on that question.
No, that's a great start. And in fact, I'm thinking, so James Mahoney has a question here that probably will allow you to kind of build on what you just said. He's interested in your thoughts about concretely enacting your open science vision. And his question is, how do you establish collaboration in science and further open up the playing field to include more people without, quote unquote, spinning your wheels, lots of time organizing the logistics and bureaucracy of collaboration, as opposed to conducting research?
Yeah, it's a very timely question, I think. Over the past 3 years, when our world was turned upside down, I think we all saw that we don't necessarily have to get on an airplane to have a productive meeting. There's nothing like being at the blackboard for me, collaborating with a mathematician. That immediacy of being present is important. But we can do a lot through these virtual means. And then once you open up the virtual means, it also changes the nature of the interaction. So for example, in my discipline, um, at the end of a seminar talk, there's kind of a scrum near the blackboard where you're trying to talk to the visitor about the latest advance, and you're trying to understand where the questions at the research frontier sit. But that space, which I have felt somewhat comfortable to be in, sometimes very intimidated by, but looking the way that I do and being the gender that I am, I have felt the privilege, and I didn't quite appreciate it as privilege, to be able to go up into that scrum and participate at the research frontier questions. But in the Zoom world, or in this WebEx world, we have a new way where there's engagement. It's not just at this moment at the end of the talk. There is this chat. There's people that might feel insecure and they don't want to show video, but there are ways where they can participate. So I guess building into the question, I would say that the digital tools over the next 10 years are going to create new ways for people to interact with science at all levels. And we should design these digital tools with the terms that are popular in the startup world, like gamification and virality, to try to create opportunities for people to come into the scientific enterprise. Another aspect of that, though, is these tools are also being used against us as scientists. I think about what's happening with, say, the IPCC reports and all of this work by CMIP. Has any area of science ever been peer reviewed as hard as the evidence for climate change? We as scientists, I think, are bowled over by how powerfully we have scrutinized whether or not there really is a carbon signal in the climate. And I think by and large, the scientific community is overwhelmingly convinced this is real and scary. But someone can just take a poppycock answer and say, oh, that's your opinion. And so we have like a crisis where validated information that the scientific community endorses is not cutting through the misinformation. So I think with those kind of framings, this question is really, it's not just about technology. It's also about the role that technology plays in elevating scientific knowledge relative to bullshit.
A great point. I'm just grinning here. We have a question from Amanda about your ideas on how scientists can be encouraged to engage in open science, sharing data, algorithms, code, ideas, etc., when several scientists have a fear of being scooped, which could negatively impact their future funding. And I think it goes to one of your earlier points about some of the tensions you see.
So I guess my first question is get over it. You're going to get scooped sometimes. It's inevitable. You're going to get scooped. But if you get scooped because someone else, sorry, my daughter just called me. I put her off. So it's inevitable. You're going to get scooped sometimes. But if you get scooped because someone is working on your data or thinking in your direction, it's probably an opportunity to forge a collaboration. So if you think at, say, NASA scale or NSF scale, you have to set incentives that drive the collective forward while recognizing that competition drives the individual. So the question is asked, how do we get these individuals to participate? So I'll maybe tell you a vignette about my own experience in the process of Syzygy Callisto to 2I2C. So as Peter mentioned at the top, I started in this kind of digital plus social world by starting CrowdMark, which is a venture-backed, for-profit education technology startup. So I think about things like moats that protect my special secret sauce so that I can sell something to a customer. And then we propagate forward, and 2I2C emerges as this idea, this thing that we're going to try to build. And one of my co-founder collaborators and a truly inspirational person, UV Panda, said, I like this 2I2C idea, but I won't do it unless we are willing to do it under this right to replicate. And my initial reaction to the right to replicate was, wait a minute, you're going to try to federate a process by which our customers can leave our service and become independent operators of what we had provided for them previously. It's like shooting ourselves in the foot. And we discussed it, we debated it. I was worried about it. But what emerged is the right to replicate is a business continuity plan, a new kind of business continuity plan for the folks that we serve. It's also a diversification of talent strategy so that new people that learn how to do what 2I2C can uniquely do right now emerge, and the entire ecosystem of interactive computing for supporting science is improved and enriched. And so I've gone through this process multiple times as I've moved from kind of thinking with my for-profit entrepreneur hat to trying to think about what it means to be an open scientist. And almost every time I feel the perception of competition, I have found a way to enlarge my goals, to look to my overall mission, to think about what kind of impact I want to be a part of in my future. And inevitably, that expanded view of my role in whatever I'm trying to accomplish leads me to turn competition into collaboration. And so I suggest that anyone that's worried about getting scooped, is probably worried about next week or next month. But if they think about their impact 5 years from now, getting scooped might be the best possible thing, especially if you get scooped with these notions of humility and generosity, and you celebrate the person that scooped you, and you find ways to get them to do your next question faster. If you have no questions or research ideas other than the one that you're worried about getting scooped on, well, maybe you need to do some more thinking. I just think we need to get over it because science is a collective effort and the goal is to advance human understanding, not your career.
Interesting. It seems to go to the monotonic conservation point that you made early on, and in a sense, you're talking about a shifting to a non-monotonic reasoning, something where you say, hey, it isn't about the surprise tomorrow. It's about what might come out at the end of the tunnel in another few weeks, months, or years.
So I want to push back slightly there. I think it's
Okay.
extremely monotonic in the sense that when we work all together, we work better. And if we could find a way to get over our selfishness and instead work generously together, I predict that the global effort of science is going to go faster, and our knowledge about ourselves and our knowledge about the universe are going to go faster. So it's a monotonically increasing bet. Every time we've eliminated selfishness and found a way to collaborate, good things happen for the collective.
Mm-hmm. Great, thank you. I want to go back, if I can, to some of the framing questions that and I know you did a fantastic job of kind of speaking to them, but I was wondering if we could turn back to those just for a moment. So one of our areas of interest is user needs and business needs, and I think you've talked to user needs and also some business needs in a really innovative and an insightful way, kind of challenging a number of us to think bigger and differently. Are there particular user needs or business needs that you would lift up from the ones that you talked through earlier?
It's a good question. So a couple of observations there, I guess. I think that there is a new kind of user, let's say, is emerging. Someone that doesn't know how to make an SSH pipe sing, and they don't necessarily know all the bash tricks, but if you put them in a browser-based, JavaScript-rich environment like Jupyter Lab or RStudio, they can make advances. They can participate in data explorations and learning. And I think there is a bit of a sluggishness because folks that know how to do old school HPC stuff have these really powerful tools, but in a way that is characterized by my colleague Yuvi that I referenced before, they're accidentally complex. So it's accidentally complex if you want to do something with ML or AI that you also have to be able to sing bash and play around with a Unix terminal. That's not necessarily a prerequisite to do things that you want to do with data. And so I think a user need, if you will, is to think about different classes of users who want to do specific kinds of things that right now have to learn a bunch of irrelevant things to do that. And so if you can streamline the path for a user who wants to do X without having to learn A through K, then I think you go faster. A second user need is I like reading people's work. After they've done something, I like to read it, but I'd rather play it. I'd rather push play and see the data that they used live. And so I think there is a need to think about the output of science, the research products, the computational narratives, the PDFs that we sometimes generate are going to be replaced by new things, new format, these executable articles that you hear people talk about. And so I would encourage you to think about that's a new use case, and everybody who's a reader might also be somebody who wants to interact a little bit with the data. And so that's a different side of the tool chain, the data tool chain, if you will. But it's a side that I think is going to speak to openness, validation, reproducibility. And if you make these research products more composable, more like Lego blocks, then more can be done.
Great, thank you. We have a question from Richard Berry. Hubble Space Telescope is considering going to zero proprietary time for data. Could you comment on what you see as implications for scientists who proposed the observations?
So I don't have enough familiarity with Hubble. Maybe you can tell me, Peter, or maybe Richard can chime in. The hypothesis about this change, can you explain how the time allocation on Hubble is previously versus the next scenario?
I'm not, let me see if there's someone who wants to come in. My understanding is what he's getting at is that there are scientists who originally proposed the observations and they would like to be able to work with those before they immediately go out. So no proprietary even for those who proposed it.
I see. Okay, I think I understand now. So, so I think of so Yosemite is a beautiful place. The national parks are beautiful places. And we built the National Park Service so that people can go and check them out. I think that the Hubble Space Telescope is kind of like Yosemite. It's a beautiful thing. And it makes incredible pictures, incredible data. It's an anchor for massive scientific discovery. But it's kind of like the national park. And I think NASA should build systems analogous to the National Park Service that allows for to use, discover, and understand. So I think that putting filters on who can see the data has to be the default no. It should be default open, and you have to have really good reasons to close something. But to be proprietary so that you can take your first look and discover the exoplanet that you think is there because you want to publish first, I think NASA should be really cautious about that. I mean, we want people to get their credit for making discoveries, but we also want people to participate and share in the discovery process. Look what you guys do with the landings on the rovers. The whole world celebrated, right?
Can the whole world celebrate when somebody makes a new observation with Hubble in a new way?
Very good. We have another question from Mike
I've
Little.
lost audio.
Oh. Do you have it now?
I don't know if it's my headphones. Can you still hear me? I've lost you.
I can hear you. Are we back?
I'm back. I don't know what happened. I lost my headphones, but Bluetooth came back. Okay.
Very good. So we have a question from Mike Little. It seems to him that helping people form multidisciplinary teams to do research, particularly involving domain scientists with computer scientists. I'm sorry, I missed. I'm missing the question here. So
yeah, I think I understand the question.
he's wondering about thoughts how to do that.
So it's hard because a lot of times computer scientists want to do computer science, which is beyond the implementation of existing compute and compute ideas in the context of another discipline. So, you know, somebody that's working at the bleeding edge of computer science may not want to clean data for you so that your data is now cleaned and you can make advances. So it's difficult to make the computer scientists who have their own research engaged with your research agenda. But I think what emerges instead, you know, every provost and every vice president of research has been trying to promote interdisciplinarity for forever. And they throw out some carrots sometimes, and occasionally pairs of people collaborate. But I think what's emerged is a new strategy, and it's, you know, you also see it in the sort of decade-long visions that are coming out of NSF and other sources, is to think about convergent research, grand challenges, system science style ways of bringing together large questions that can only be approached with a Manhattan Project-like team. And then there are authentic reasons why a computer scientist who's concerned about climate change might want to talk with a climate scientist to work on things. So I think you have to unify the incentives in a better way and not just try to force somebody who's got certain special talents to work together. I see comments from Richard and Rebecca that I think are really important. So absolutely, I think that there is a significant risk to new scientists if we're exceedingly open, and we have to find the way to thread that needle. But I think that the default right now leans more towards protection and less towards acceleration. And we have to find the right way. So absolutely, we need a fertile environment so that young scientists can emerge and become associated with results. But the current model of sort of king PI standing over a giant hierarchy of junior scientists, I think is also not the right model. And maybe I'm taking a more polemical or strong perspective that runs some risks in the ways that Richard and Rebecca have described. But I'm leaning into that and trying to push us towards openness while at the same time having that humility and that generosity to protect the younger generation. And I don't have all of that worked out, but I think we absolutely have to lean towards openness and research acceleration rather than being super cautious and trying to protect. But once you have protection, the people that tend to be protected the most are not the young scientists that we're worried about. I think it ends up protecting the PIs more than the young scientists. And we have to break down some of those barriers. But I don't have the governance worked out. I'm trying to stimulate conversation rather than propose solutions.
And it looks like you have definitely stimulated some interesting conversation around this, and Richard Berry is thanking you for that. Yep. One of the areas that we've been struggling with is sort of best practices for open source science architecture, data computing infrastructure, and operation. And what you've done a really nice job of is really talking about, not so much or even a focus on the technology, but sort of the broader, the pieces that the technology enables, the community, the education, the growing of the community, the growing of the endeavor of science. Are there particular best practices that would, in your mind, help make that happen?
Yes. So let me first just react to that. Like in math departments, we don't have labs typically. So we tend to get crushed when it comes to space in university space allocation. So we've tried to make arguments that we have an interaction chamber where we stand in front of a blackboard, and that's where we do our pure theoretical research. And so we try to make these arguments that the enterprise of mathematical research requires infrastructure like blackboards and seminar rooms, and those infrastructure investments that a university might provide to us are analogous to the labs that a chemist requires to do her research. So separating technology and infrastructure and resources from the enterprise of science, I think, is a mistake. We have to think about the entire collection of all of the tools and ecosystem necessary for the people-to-people engagement that leads to advances in human understanding. On the use of technology as infrastructure for facilitating science, which I think was the heart of your question, I think a very important best practice that I would say NASA is popularizing, promoting, and providing a motif for is the code of conduct at the top of the discussion. So defining what it means to be a scientist includes defining what it means to not be a jerk. I go back to sort of the first land acknowledgement, if you will. So when we call ourselves academics, we are really paying homage to the Grove of Academus, which is the place where Plato stood up the academy. And in one of the walkways, or so the lore goes, when you walk into the Grove of Academus in Plato's academy, there was a sign that said, "Let no one who's not a geometer enter here." So back then, geometry really meant earth measurement. And here I'm talking to people involved with earth data systems. So in many ways, I think that you are the successors, the folks that have emerged from this earth measurement model that goes back to the Grove of Academus. But another part of that mantra over the entryway into Plato's academy, it's not just about earth measurement or geometry, it's also about going in there is an indication that you expect that logic and arguments about ideas are first and foremost, and that you will participate in the scholarly exchange of ideas with the right type of attitude and the humility that you might be wrong. And so I think that when it comes to building technology, you should constantly focus on the role that technology plays in facilitating community behavior, leading to these advances in science. And it goes back to the foundation of the academy, a la Plato, that evocation of we all know what it means to write a geometry proof, and we're going to allow ourselves to convince others using those kinds of arguments rather than ad hominem attacks or being a jerk and so forth. So I think part of the best practices really focuses on creating the right environment for people to participate.
Thank you very much. We have a question about new science models. Are you familiar with a model like Kaggle?
Yeah, so
Something
data
you could
science
speak
as a
to?
sport. Yeah, I think that's really interesting. So I was actually reflecting on this while I was studying to kind of prepare the talk. So one thing that I learned about is military intelligence. So imagine that you are the admiral or you're the general, and you have a group of data scientists, experts, policy analysts that work underneath you. And maybe your only job in the military as this leader is to understand the logistics related to, say, fuel supply for your enemy. So you're not caring about a lot of other things. You're really focused on that specific actionable insight. So there are large structures in military intelligence that are designed to support these types of decision makers with a collection of folks who gather data, who gather expertise, who build briefs that answer very specific types of questions. Another example, the CMIP process. So a group of leading climate scientists get together and they kind of define a league. They define a collection of metrics that they will use to judge each other's models and each other's work. And they agree that this is how they're going to do these sorts of evaluations. And in so doing, they kind of set their objective function and they work well together. So Kaggle is kind of similar, where either Kaggle or others that partner with Kaggle can specify a grand challenge problem or a data science problem, and then people can compete and build answers and research products in that direction. So I think these models are extremely interesting. In contrast, I think there are these concepts that are also extremely important, especially in the university context, like academic freedom. So the freedom for me to explore whatever I want with my scholarly training and my scholarly expertise is extremely important. And so we don't necessarily want to define fettered research targets through kind of grand challenge expectations imposed on scientists. We have to enable this kind of basic curiosity-driven side of things. But I also think that these notions around convergence can maybe bring together people in new ways.
Great, thank you. I want to go to one question here, but before I lose my thought, we had a question that several of us, I know I was interested too. Could we get that bit.ly link to the talk again, maybe in the chat, or if you could just put it up, folks could get it down. Really appreciate it.
I believe that's the link.
That
can someone
looks
check
like what I remember.
Can someone check just to confirm while I'm trying to like not write in the chat
Okay.
and answer questions?
Great, thank you. You have talked a lot, really nicely about emerging issues and opportunities, and really challenging all of us to lean forward and think forward and downstream. Are there particular emerging issues that come to mind, maybe even ones that you haven't mentioned yet, that you really want to leave with us at the close of the talk and say, hey, these are some key things I've been thinking about and seeing?
So yes, one thing don't have proper permissions. Let me see what I can do here. Let me try to resolve this issue with the link real quick.
Sure. And just so everyone knows, we will resolve this and get it to.
Here's the expanded version of the link.
Page.
There's the expanded version of the link. That should work. So
great. Thank you.
So I've been really inspired by a technology experiment called MyBinder. So MyBinder is an ephemeral Jupyter service. So I can build a link, and with this link, I have a software environment specified. I have, say, a collection of Jupyter notebooks or maybe a single Jupyter notebook. And I can make this link shared with Peter. Peter clicks the link, and then in the back end on commercial cloud, a virtual computer is assembled with the necessary software and compute environment to render the software product, the Jupyter notebook that I created. And then it allows Peter to work in my wake, to work on my stuff in an ephemeral way. I think this is game changing because it allows us to take research products that you would normally just read, and now instead of just reading, you can interact with them and play with them. So the pioneers that built this did so with incredible generosity and on some commercial cloud credits. But there's no effective, it is catastrophically successful. There is no sustainable method right now for us to maintain commercial cloud tool chains ready to be deployed ephemerally for readers. So I'll fix up the 403. I don't know what's going on. I'll figure it out. I'm concerned that we have this thing that could potentially be a way to mobilize NASA data with analysis for folks that are just a little bit more than curious to read, but they want to kick the tires. And we don't have a proper sustainability model. In a similar way, I have this project called Callisto. So Callisto builds open education resources on top of Jupyter that are designed for students and teachers in grades 5 to 12. It's pretty awesome. And anybody that has a Google link or anybody that has a Microsoft account can log into our hub. Now there's a terror there because we have had problems with people going in and doing coin mining and crypto mining because we have this publicly accessible cloud instance. But I've learned that by making things more open than I really feel comfortable with, I'm sometimes hitting these obstacles where somebody's trying to steal from me, but more often than not, I'm finding the people are accessing it, are using it, and it's growing, and the mission of sharing is advancing. So I think one of the bits of advice that I would say, I know that NASA is a United States entity, and as a boy growing up in Texas, the moonshot was like transformational to me. But NASA is not just America. NASA is like human civilization's maybe greatest achievement to date is landing on the moon. And so NASA's leadership on open science and kind of brand for the universe is ours as humans to understand. I don't think any organization in the world is pushing that forward more strongly than NASA. So leaning into and NASA's outreach and inspirations for learners is just incredible. But leaning into that a little bit further and making compute somehow be available so that others in NASA's influence wake can participate in the science in a more interactive way, I think is a huge opportunity. I feel like Binder is a showcase for what might be possible, but it's a showcase that doesn't have a proper sustainability strategy. And so I encourage NASA to think about these wider audiences that you inspire and might be able to bring forward faster in this open science future that we're building together.
Wonderful, thank you. And I'm kind of thinking that's you've planted a flag out in the future for all of us that is just really appreciated. Jim, I've really enjoyed listening to everything you've had to say, and certainly the opportunity to be the face next to yours has been really nice. I just want to thank everyone for bringing the questions forward that you have been able to bring. Let me see if there's anyone, maybe Mike or Elena, any questions or thoughts you have. I know I want to turn it over to Elena in a moment just to close things out. But I'm not seeing any movement there. So Elena, why don't I turn things over to you? And Jim, again, thank you very much on behalf of the study, but really the whole audience. Just really appreciate it. Elena?
Yeah, I just want to thank you so much for coming and speaking with us and for your very interesting insights. And also thank the participants for their questions. We really, really appreciate everyone's participation and attendance at these meetings. So thank you so much. And we look forward to talking to you soon.
It was a great honor. Thank you for the opportunity, and thanks to the audience for the awesome questions. So we have to fix up this 403 error. So I will communicate through back channels with Peter or Hannah or Elena, but I want those slides to become made available, but I don't know what's wrong right now, but we'll figure it out. Thank you all.
Well, thank you so much.
Very
Really
good.
appreciate it.
And can I mention, folks, I completely forgot to circle back. We do have a talk coming up tomorrow, and then another one on Tuesday. Oh, Hannah's bringing it up for me. Thank you, Hannah. Tomorrow we're going to hear from Esri. Next Tuesday, the European Euro HPC. And then when we get into November, Carnegie Mellon Software Engineering Institute. Those are the 3 next ones we have on our schedule. Jim, you would be more than welcome to join us. They are definitely open, but we hope to see other folks there too. And thank you, Hannah, for bringing that up.
Thank
Bye,
you so much,
everybody.
everyone.